Hi, and welcome to our next session here on maximum likelihood estimation and how that actually relates to empirical risk minimization. So here we'll figure out, it's going to be very hard to see, that what we do when we do pointwise optimization of the maximum likelihood principle, that this is exactly the same as doing empirical risk minimization from a machine learning perspective. So what we do in statistics, in many cases, I guess mainly from the frequentist perspective, is very, very much the same as ERM. Okay, so there's really not a big difference. I'm going to make that very clear, mathematically very clear in the upcoming slides. So if anybody wants to tell you different, don't believe them. I guess also maybe just take a look at the formulas, maybe show these to them. We will see that there's a very strict correspondence because between assuming a certain distribution in errors from a statistical sense, in a statistical sense, from a statistical perspective, and assuming a certain loss function and minimizing that in ERM and machine learning. Machine learning is statistical learning anyhow, right? I guess there's statistics in the name, and we're assuming distributions and so on. So I don't want to get into philosophical discussions now. What I do want to do here in this session is I'm going to show this correspondence mathematically as clearly as possible, and then we'll learn certain correspondences for concrete losses and error distributions. So we'll figure out that Gaussian errors basically directly correspond to a L2 loss minimization, and one loss minimization pretty much assumes Laplacian errors. We'll also take a look at nulli targets and then see that this is strongly connected to log loss minimization, and how this works out in general I'll discuss in the end. So as always, some of these things are a little bit easier to explain for certain scenarios, so I'll start here with the regression because that's the easiest. As always, I'm going to assume that my data comes from some underlying data generating process, some joint distribution, capital P. And as usual, we've seen this before in the beginning of this chapter, and this is something we very regularly do in statistics, is when we want to model stuff, we take a conditional perspective. So we reason about what is the distribution of y given x. We've done that all of the time here in this chapter, and this is also very, very common in stats. So, and this, if there's like a joint distribution of x comma y going on, then there's certainly a conditional distribution that I can compute from that of y given x. And that's going to have some form of a density, right? And that density I'll just denote here as usual with a lowercase p. And yeah, that's going to depend on x, and I do want to learn something later on about this. So at some point I'm going to assume some form of this, and I'm going to assume that this is going to be parameterized with a parameter vector theta. And usually one writes this down even slightly differently. So the usual way to specify things here is to do something which we often call a surface plus noise model in statistics. So we say that our y as a random variable, well, y conditioned on x, can be written down as y equals some f true of x plus some random noise variable epsilon, okay? So this surface plus noise model is called like that because there's like a true surface going on, and that's this f true thing here, and then there's some random noise we're adding on top of that. Look at virtually all of my, I don't know, simulation examples here in this lecture. I'm always assuming some functional form which in the background which I don't know, and then I put some Gaussian noise on top of that or whatever, and then I sample data from that. And this is exactly this conditional sampling perspective here, this conditional specification perspective, which I'm assuming here, okay? So the thing is, f true, let's maybe make clear what is like random and what is constant here. So the f true is some constant function. Well, maybe I shouldn't say constant function, it's a function, but a non-random function, it's just a function. The x I'm conditioning on, so that's also not really random here. But the epsilon is a random variable because that's random noise, and I'm going to assume that this epsilon in general is also independent of x. yeah, if I would look at X as a distribution here, marginal distribution from this capital P, and usually also my epsilon is going to be zero mean. And it could be Gaussian. We'll actually discuss that in a few minutes, but it doesn't necessarily have to be, and we'll discuss that too here. And the idea is now that, of course, we want to learn what f true is, right? Or what the parameters of f true are. So again, these parameters will then be this theta vector, and that's the part of the distribution P I'm interested in. So just have suppressed this here notation, but that's what I want to learn. Now, how would I do that if I would have done some basic course in stats before? Well, there's a maximum likelihood principle, right? How does that work? So I'm assuming I have some data which is sampled from my underlying data generating process from my distribution. You can already see that's exactly the same assumption that we have in machine learning. Now, how we now figure out what our function is, that works, at least at first glance, a little bit differently. So we use this maximum likelihood principle. What is that? That just says, hey, how about we write down our likelihood function, which is just the multiplied likelihood of all of these independent data points under our assumed likelihood function, and then we want to maximize the parameters so that our data the optimal parameter vector should actually maximize this likelihood so that, yeah, our sampled data matches our selected parameter vector best, right? So I guess what I've put on the slide is the most compact formulation, right? We maximize our likelihood so that the data is most likely under this, yeah, optimized parameterization. Yeah? Data becomes most likely under this parameterization. And I'm using this weird L here to, I don't know, use a different symbol which still uses an L, but which is not the L for our loss function. But as you will see, I'm not sure whether, as you will see, this is going to be something that's pretty much equivalent anyhow. It's not exactly the same, but we'll see the connection in a few seconds. It's really going to be easy to see. So this is a product, right? So I'm right down here this product of when I insert all of my data points, xi, yi, into this conditional density P, and because it's a likelihood, it's likelihood terms, not really probabilities, but something similar, right? So I have to multiply all of them together to get the joint likelihood for my IID data that I've empirically observed. Now, I want to optimize that, right? I want to maximize that for theta. This theta is this parameter thing here in my conditional density. But using products is annoying. Maybe I like minimization a bit better because it's my default for optimization. So I just take minus log of stuff. And then we have this negative log likelihood, and that is what statisticians usually also look at if they really want to practically optimize this thing. And I guess they like looking at this anyhow. So I now just do minus log of the thing above. That will not change one iota in terms of what I will get in the end in terms of a minimizer, in terms of an optimizer. It will turn this maximization problem into a minimization problem because of the minus. And the log I can now push inside of the product, and it will turn this product into a sum. So I have now a sum of these minus log density terms. Okay? And that's what we call the negative log likelihood, NLL. And it will turn something like this here into potentially something like this. And we'll see a few examples now. And this we can now pretty directly already identify with empirical risk minimization in machine learning. So in machine learning, we just take a very slightly different perspective. Instead of conditional distributions, we pick loss functions, right? And maybe you find this a bit more intuitive. I have to admit, when I was younger, or maybe I still do that. So you think about, hey, I have a prediction going on, there's a true label. How do I measure the difference? Okay, I just have to measure differences somehow. And I write down some nice little formula for that. Instead of thinking about, my data is potentially normally distributed, it has some other weird distribution. do I really know that? How do I check that? How I measure prediction errors, that seems to be quite intuitive, especially if you, I mean, you have to understand your modeling task, so to speak, your prediction task anyhow, and if you don't know how to measure errors there, I guess you have a problem, right? The next thing we need in ERM is we need, like I told you before, some form of hypothesis space, so our function can't be completely arbitrary, at least not if we want to like practically solve this ERM thing, and we call that space of parameterized functions, we call that a hypothesis space. But in statistics, this f-true thing here, there's something about this as well. So we also don't do this for arbitrary functions. I don't want to go into parametrics versus non-parametrics now. Both of these are covered here by what I'm discussing here. Yeah. The thing is, in statistics, they have to do this as well. They just don't call this hypothesis space, but they still assume some form, some functional form. Yeah. Maybe more often simpler models, but like I said, non-parametrics exists too, right? Okay. And now the only thing I'm going to do is I'm going to say, if I have this conditional density here, I just do minus log of that, and I call that a loss function. And the loss function has two arguments. It has this y, I mean that appears in my conditional density anyhow, and the second argument is this f, my prediction model. And we said that this f true here, that actually specified our probability model, right? So that has to appear somewhere in our conditional density. So it's pretty much possible to write this thing here in terms of this f, right? It must appear somewhere, otherwise this surface plus noise model wouldn't make any sense, right? Or it's a direct consequence of that. So just do minus log of this stuff, and then I just call that function here my loss function. That's it. And if I do that, and now look at this negative log likelihood, and just write this in L, this is empirical risk minimization, right? It's exactly the same. Yeah? There is no difference. If I'm now minimizing that for my f, I'll get a certain result. If I do maximum likelihood, I mean, it's going to be the same, and it cannot be anything different, because the only difference is that, I mean, for the one problem I started on, I don't know, this likelihood scale, and then I did minus log of stuff. And then if I look at this minus log of things, I mean, it is ERM. It is exactly this. And I want to look at now at a couple of examples to make this even clearer. And because I'm only interested in identifying the location of the minimizer, I don't really care too much about certain constants. So if there are positive multiplicative constants, I will just drop them silently, because I want to be lazy, and compact and short in notation and general additive constants I'm going to drop as well, right? Both of these things, they don't change the location of the minimizer. So how about we just look at an example here where we have this f true, and we have our epsilon, and let's just say our epsilon now is normally distributed. It's Gaussian. I can then immediately figure out what the conditional distribution of y given x is. So this is also going to be a normal distribution, because this thing here, well, this is normal, this is constant. So adding these two things up will actually it will not even change the variance. We will certainly not leave the class of Gaussian distributions. And the only thing that's going to change is that my zero mean of epsilon is going to become f true of x. And the sigma squared, so assuming homoscedastic noise here, is staying the same. So now I look at my likelihood thing, and I'm just going to insert my Gaussian density, which I will not read out, and I have already dropped normalizing constants here, which you can also infer for me using this proportional sign here, which is going to become a good friend of ours, so we can just drop terms we are not too much interested in, and that just annoy us. Now I do minus log of things. So let's just concretely do this. So here, you see the minus log. I now push this inside of the sum. The product. But the product is going to be turned into a sum. And then I have this exp function here, and log and exp, I don't know whether I should say they're good friends or they're enemies, but they nicely cancel out. And then there's here this minus thing, and that becomes a plus. And then this here is going to be a positive multiplicative constant. So I can just remove this, I can remove this, I can remove this, I can remove this. Ooh, and what's left? This. And that looks very familiar. This is ERM with L2 loss. Now you can see this is just risk minimization with square loss. If you've ever, I don't know, done the derivation for something like ordinary least squares, this shouldn't be a surprise, come as a surprise to you. It's pretty obvious. It's this inner part of this density that remains when you do the negative log likelihood. Yeah, it's exactly the same than us saying have some model F. It's linear, it's a neural network, whatever, and I optimize that with respect to L2 loss. It pretty much means that we're assuming that these additive errors here on top of our surface model, and our surface model is just like something that comes from this hypothesis space we picked, that these errors are actually normally distributed. And you might like that assumption or not. The thing is, you are operating under this assumption if you say I'm minimizing L2 loss. Yeah? That's a choice you're making, and it just might be a little bit more hidden to you before you have listened to this session, hopefully not afterwards. Usually I'm a big fan of showing these things empirically with little examples. I guess I'm not violating this principle here. So I'm now simulating some simple data, which looks like this. So I was very lazy here, so I used a very simple model, just like 0.2 times x, so univariate feature. There's some additive noise going on that has a variance of 1 and a 0 mean, and it's of course Gaussian because that's the example that I want to discuss here. So I'm now fitting a linear model with L2 loss, and I'm going to compute the empirical residuals for this linear model fitted with L2 loss on my data, on my simulated data, some test data set. Maybe I guess I'm doing this on the training set, I think. Yeah, I have forgotten this. You can look the source code up because everything here is open source. Yeah, I guess I'm doing this on the training set. And I'm now computing all of the residuals. And how about we just plot them and take a look at a histogram of them. And there's also the L2 loss in there for reference, I guess. I don't know, it's a little bit apples and oranges plotting this in the same plot. What I wanted to show is that like where the residuals like mainly located at, and you can see here that they are like more located. Well, I guess what this actually helps you to do is you can now think about how the risk for this model is actually computed. So that would mean, so you like look at a little bar here. So that's like the probability of having these residuals, and like the height of that bar, and you kind of have to now integrate out your loss at that bar. Yeah, you multiply all of these heights with the loss values here, and if you do this across the whole histogram, you get the risk of your linear model that you're looking at here. Which actually I don't want to discuss now. What I do want to discuss is how about we just look at the thing, we look at the histogram, and we think about what shape that could have. And maybe I should have actually plotted that. I should have maybe plotted the density of a normal distribution over the histogram. And then we could have compared that and we would have seen that this looks very similar. Maybe I'm now doing something that is as good. And that is I'm plotting here a QQ plot. And a QQ plot is a nice tool to compare empirical distributions and to compare an empirical distribution against certain theoretical quantiles. So I'm doing that. I'm comparing that to my normal distribution that I'm assuming for the errors. And if my empirical data points here are like nicely located here on this main diagonal, which they are, then this is like good evidence that my residuals or these empirical data points actually come from this theoretical distribution. So my residuals here are actually Gaussian when I optimize my model under L2 loss. And this is exactly what we expected and what I wanted to show here. And we can now vary this a little bit, and we'll do this a little bit faster because it's just going to be exactly the same thing as before. The only difference is now, I'll now assume that my epsilon here, so my random variable which encodes my noise, my additive errors, let's assume that this has now a different density. So it's a Laplace density now, which you may or may have not seen before. It looks similar to Gaussian, but it has this like absolute value going on here. And I guess you can already take a guess where this is going. Yeah, plotted this here. Yeah, it's a little bit more peaked because of this absolute value and because I'm not really using the square. And let's again do maximum likelihood and then do negative log likelihood. And like I said, I'm now going to do this faster. So I'm writing down maximum likelihood. I'm inserting my density. In this case, it's the Laplace. I do the negative log likelihood of this. I remove all of the constants. And what remains is this. And this is ERM with L1 loss. Hopefully that was not too fast. You can do this with pen and paper. You can drop all of the constants yourself. But it's not hard to do this because it also looks very similar to the Gaussian case. Yeah. And you can do this also for other loss functions. And now begin to think about this, what happens there. So maybe you're using now more, I don't know, exotic loss functions. I don't know, you could, for example, think about the Huber loss. And this is a little bit harder than to identify that with a distribution. But you can actually show, and again, this is potentially not surprising because the Huber loss is a combination of L1 and L2, that this is a hybrid of a Gaussian and Laplace. And I've linked a paper here on the slides where they discuss this way more in detail. Here's my simulation. I'm now using exactly the same setup, but this conditional distribution here is now going to be Laplacian because my errors, my epsilon variable is going to be Laplacian, and I now fit a linear model, but now under L1 loss. I don't know, we might have even, I can't remember that. I think maybe we even had to program this ourselves. Maybe this is also why the, I don't know, QQ plot here is not like perfectly aligned. I forgot this a little bit, but if you look at this, it works out well enough. Yeah, hopefully this is convincing enough to you. Residuals, again, approximately match my quantiles. They approximately now match my Laplacian quantiles. And the one thing I changed was going from L2 loss in optimization to L1 loss. Let's do classification now. Yeah, guess that's also interesting. So how about we do binary classification? Now my Y is encoded as 0, 1. And I'm going to make the usual assumption that Y given X is Bernoulli distributed. And there's some pi true of X going on. That's my true probability model, my true surface model. I can again do maximum likelihood and then do minus log of stuff. So here I'm going to do this a bit faster. So I'm already on negative log likelihood level, because why not start there? And I'm now inserting my Bernoulli model. So my Bernoulli model means, what's the likelihood thing now? So the likelihood function is, this is just, I think we did that before, right? I don't think I have to do this like super slowly here again. So we did this before when we looked at logistic regression, at the very least there. So I want to write down the likelihood of observing a Y equals 1 or 0 when I have this probability pi going on for sampling a 1. So if Y is 1, I want a probability of pi. And if Y is 0, I want a probability of 1 minus pi, right? Counter probability. So you can just write that down compactly like that. Yeah. So like I can just marry these two cases together and have them like in one little nice algebraic formula. And now I do minus log of that, right? So let's do that. I do minus log, and then the log function turns this inner product here also into a sum. And here there's no x function now, that's going to be cancelled out, so just leave the log there. Okay, and now look at this thing, and that is Bernoulli loss, log loss, cross entropy loss, however you want to call it. And we pretty much did that derivation before when we looked at logistic regression, and we did it again, I think, when I introduced Bernoulli loss. And in the upcoming lecture. I hope this is not boring to you, but I'll not show this derivation again, but I will actually show that from 50 different perspectives, you can actually at the end arrive at log loss, yeah? And connect that to different areas of, I don't know, modeling and science. Okay, so yeah, operating under this Bernoulli model and doing maximum likelihood is the same as saying I am optimizing cross entropy or this log loss function in machine learning. The one thing why I needed to do this before is for these other error functions, like, I don't know, L2, L1 and so on. I guess you can just like plausibly argue for them that they make sense. For this function here, I don't know. There are various ways, like I said, there are like 50 million ways of arriving there. And many of them require us to, I don't know certain things. So I could have derived cross entropy, but that requires us to understand information theory, which I will discuss here in this lecture, but just later. And so I still, for me, like the easiest way of arriving at log loss is from the Bernoulli model. Yeah, I don't know of any faster way. I mean, it depends a lot on what you've studied before, right? So let's wrap things up. Now, the good news is that pretty much for any error distribution, you can do this as long as you can do minus log of stuff, which you should always be able to do. You can derive an equivalent loss. So you just do that, right? By taking minus log of things. And as we have discussed, this is not new information. This leads to the same point estimator as maximum likelihood when you do empirical risk minimization. The other way around not necessarily always works. It works for many losses, but not for all of them. And the problem is that if you want to go from a loss to a probability distribution, you have to do this like minus log of things in reverse, which means I guess you have to take an exp. But then the result of this cannot be some arbitrary function. The result of this must be a proper density. And there are some prominent examples, for example, the hinge loss. We can see that the result is not really going to be a density. You can still do some form of probabilistic interpretation of this if you, I don't know, are willing to, I don't know, squint a little bit or, yeah, take a very certain perspective that I don't want to go into now. And there's a nice paper, which is now a little bit older, by Peter Solich, where he looks at that and you can potentially identify some form of probabilistic interpretation of hinge loss. But yeah, you have to do this in a certain way and it's not super direct. So there is a certain class of losses where you can do this reverse way and you can identify a probability distribution with it. So if your loss is distance-based, and with that, I guess I'm talking, you can do this for classification as well, but maybe just let's think about regression here. So you can just write it as a residual, or in terms of the residual. Yeah, I guess nearly all of the losses we have discussed here, it was possible for them. And ignore the capital pi, p, and it's going to be just the distribution we're going to associate that with. We can actually say that empirical risk minimization is fully equivalent to this maximal conditional likelihood thing with a certain distribution p. So this is identifiable if log of p of r, or yeah, I don't know, the log of my conditional density is an affine transformation of my loss function. Yeah, so this is basically, yeah, either you do exp of this or you do log of that, doesn't really matter, so bring them on the same scale. And then one must be an affine transformation of the other, which was like this thing of me dropping constants before. So also this is, I don't know, pretty much just saying that everything we did before has to work out. So this is not a very surprising or creative, I don't know, assumption. Yeah. And then this P must, of course, be a PDF. So if this here holds, yeah, I guess it just says, like, if you can identify something with your loss function, then it does work. Maybe this is not super insightful, but it's, I don't know, the algebraic requirement. Yeah, and then this works. So for these type of loss functions, we can do this identification. You can do the reverse, and you can identify a probability distribution. But I don't know. I don't know whether your perspective now is going to be, ooh, there are some nice cases where I can actually work with the loss function, but I don't necessarily have to have a probability density here. And for that reason, ERM is slightly more general, if you want to put it like that, and more precise about what that means. I guess that's all right with me, and that's fine. So from that perspective, you can do a little bit more with this. The thing that I like most usually about this is that I don't know. Like I said before, I have an easier time thinking about losses, thinking about differences, thinking about these things more geometrically. I do enjoy a lot that also now, yeah, when I started studying this, that I can now make this connection to probabilistic models. That's pretty great. And it's always good if you can look at things from different perspectives. I guess I'm starting to ramble here now. We are at the end already of the session here, of the, I don't know, the real content. So I'll stop things here. Hope I will see you in the upcoming sessions. I hope you enjoyed this a bit. I hope you learned something. Bye-bye.